Hello there. In this video, we're going to present a proof of a very classical example, one that pretty much any math major should be able to present to you, and that's the irrationality of the square root of 2. So recall that the set of rational numbers Q is the set of all numbers that can be obtained by dividing two non-zero integers, namely a over b, such that a and b are integers with b not being equal to 0. So the theorem that we're going to prove in this video and explain in detail is that the square root of 2 cannot be represented as the quotient of two integers. Alright, so before we actually get into the proof of this theorem, I just want to illustrate just a couple little tools that we're going to use throughout this proof. So the first little theorem, or some people call these lemmas. So for all rational numbers, a over b, there exists alpha over beta, also in Z, such that a over b is equal to alpha divided by beta, with the greatest common divisor, or the greatest common factor of alpha and beta being equal to 1, which is just a fancy way of saying that every fraction can be reducible down to irreducible terms. Right? So let's just quickly outline a basic proof for this. And this is going to require the Euclidean algorithm in case you're not already familiar with that. So we're going to let A and B be any pair of, and without loss of generality, you can choose positive integers, but that's not necessarily in this case. But let's assume they are. So then the Euclidean algorithm guarantees that there exists a k in the set of integers with k less than or equal to the minimum of a and b, such that k is the greatest common divisor of a and b. So we're going to define a over b. So we're going to divide top and bottom by k, and remember this is not equal to 0. So this is going to be a divided by k over b over k, and we're going to define this to be equal to alpha over beta. And one can easily see, so we then have that the greatest common divisor of alpha and beta is equal to 1. Now, how is that necessarily true? Because maybe alpha and beta have a common factor that's an integer. Well, if that were the case, that means k is not the greatest divisor of a and b. That means there was a greatest one, which would then give a contradiction to k being the greatest. Right? So if this is the case, then that means every fraction, or rational number, can be reduced to an irreducible quotient, alpha over beta. Right? And we're going to use this in the proof of the irrationality of the square root of 2. Alright, so let's get to the proof of interest. So theorem, square root of 2 is not in Q. Alright, so we're going to do this by a proof of contradiction. So assume otherwise, that the square root of 2 is in Q, right? Now notice we don't have a premise that is here to contradict. So that means we need to introduce other concepts that we know already is true and see if we can contradict any one of them by assuming that this conclusion is false. Alright, so if the square root of 2 is rational, then that means there exists numbers a over b in the set of integers such that the square root of 2 is equal to the quotient of A and B. And without loss of generality, let's assume that the greatest common divisor of A and B is equal to 1. Actually, not without loss of generality. Let us mandate that. We can mandate this statement, and this is extremely important, because we know that this is irreducible eventually. So let us assume that this value is an irreducible quotient of integers a over b, right? All right, so what I'm going to do is I'm going to square both sides of this expression. So I'm going to have square root of 2 squared is equal to a over b squared. And that's going to give us an expression without radicals to work with. So we have 2 is equal to a squared over b squared. Then I'm going to multiply both sides by b squared. So I'm going to have a squared is equal to 2b squared, right? So notice that this expression here is in the form a squared is equal to 2 times k, because b squared is an integer since b is an integer by closure. So a squared is equal to 2k for some integer k. So if this is true, then we have that a squared is an even number, right? So we've already proven in the previous video that if a squared is even, that means a is also an even integer as well. So let's just remember this fact just briefly. Right? All right. So another thing, so since we have that a squared is equal to 2b squared, because that's how we have proven that a squared is even, then we can also write that b squared is equal to a squared over 2, right? So remember, b squared is an integer because the set of integers is closed under multiplication. B is an integer by assumption. So that means what? So this means 2 divides evenly into a squared, right? So if 2 divides evenly into a squared, a is an integer, so a squared must be an integer as well. So that means a squared must either be even or odd. Now, since 2 divides evenly into a squared, that means the remainder, once you divide by 2, is 0, right? So that means a squared is even. So if a squared is even, then that means, of course, since E and O form a partition on Z, we know that a must either be even or odd, right? One can show that the square of an odd is odd and the square of an even is even. So we have also that a is an even number, right? So this is important, right? So what we've shown here is a is even and b is even, right? So let us go back to our premise. So we assume that the square root of 2 is equal to a over b. And what we've shown is that a is even and b is even. So since they are both even, we can write a as say 2k1 and we can write b say as 2k2. And remember, we mandated something before, right? Namely, the greatest common divisor of a and b is equal to 1. That means a over b cannot simplify, right? But notice what we have here. Notice we can cancel out a 2 out of this expression. Remember, if we multiply k by 2, that's going to be equal to a. That means k1 is less than a and k2 is less than b, right? So, of course, this just gives us k1 over k2, but this expression violates that, right? Contradiction. So, since we have a contradiction on something that we know is true, that means our premise of our contradiction proof is false, right? That means the square root of 2 cannot be represented as the quotient of integers, so that means the square root of 2 is not in the set of rational numbers, which concludes our proof. Right? So that's just a very easy proof by contradiction that the square root of 2 is not rational. And you can do this for, say, the proof that the square root of 3, square root of 5, square root of 7, square root of 8 are not rational numbers as well. And we'll get to a more generalized version of this later. Hope you enjoyed.